So calculus 1 is all about derivatives, and derivatives are simply just instantaneous rate of change. So how are we going to get to an instantaneous rate of change? Well, we need to start with a regular rate of change, and we're going to use function notation because it's good to get used to it. So this is rise over run, and just in case you're wondering why the top looks a lot more complicated than the bottom, because you could write the denominator as this, x plus h minus x, but you can see that this would just reduce down to h. So that's why there's no point in including that, right? You can't cancel out the terms in here because they have to actually be evaluated by the function, right? So these values have to get plugged into here first. So you can't just cancel out the x's up there, but they do cancel out in the denominator. So the entire point is you could apply this formula to anywhere on this graph. Like you could say, well, I want to approximate the rate of change at like x equals 1. And you could do that by saying, well, let's just calculate the rate of change from the point x equals 0 up to x equals 2, let's say, right? And you can see that that would be an approximation, but it's not going to be entirely accurate. And so basically, if you could squeeze it down to a single point, it would obviously be most accurate, or at least the closer you get, the more accurate it gets. But it is actually possible to squeeze it down into an actual single point, and you do that by taking the limit as h goes to 0. When you do this, right, obviously you can't do it right now or else you divide by 0, but when you do this with after applying or plugging in the function, it's going to give you an equation which we denote as f prime of x, but it's going to give you an equation that represents the instantaneous rate of change of this function. And so rather than memorizing the rules, though, at least right now, it's good to actually see how you would do it, right? So we're going to take all of this and plug it into here. So this would become x plus h squared h. We're still taking the limit as h goes to 0, right? So this becomes squared plus h. We're still taking the limit as h goes to 0. So you can see that the x squareds cancel out, right? And so what we're left is there. I'm going to start over just so you can see it. So we had limit as h goes to 0 of 2hx plus h squared over h. This becomes 2x plus h. H goes to 0. So now that we've reduced it all the way down, you can just plug in h equals 0 to essentially take care of this limit. That would mean that it becomes 2x. So 2x is the derivative of x squared, so we could write that as like this. And what that's giving you is that if you plug in any point up here, right, so you plug in the points to see where they go on the graph, but if you want to see the rate of change at any of those points, you plug it into here. So for example, at x equals 1, the rate of change is 2. At x equals 2, the rate of change is 4, and so on. And so this is essentially the main idea behind calculus 1. The next part involves setting this equal to 0 and seeing what special properties take place at that point.
If it takes you more than 5 minutes to apply to hundreds of jobs, you're wasting your time. Sign up at jobhelper.cc and let AI do the work for you.